Somewhere in the universe, there is a star that should not exist. Not in the sense that it defies the laws of physics. Not in the sense that it contradicts our models of stellar evolution. But in the sense that everything we know about stars, everything we have spent centuries carefully building into a framework of understanding, tells us that what this particular star does simply should not happen. And yet, it does. Night after night, year after year, this star dims and brightens in patterns so bizarre, so asymmetrical, so utterly unlike anything we have ever seen in the observable cosmos, that even the most skeptical, most rigorous, most cautious scientists on the planet have been forced to pause, to look up from their data, and to ask a question that most of them never expected to ask in a professional setting. What if we are not alone? The star is called KIC 846-2852. It sits in the constellation Cygnus, roughly 1,400 light-years away from Earth. That means when you look at it in the night sky, you are not seeing what it looks like right now. You are seeing what it looked like 1,400 years ago, when the Roman Empire was crumbling, when Islam was just beginning its rise in the Arabian Peninsula, when the Mayans were constructing their greatest cities, and when not a single human being on this planet could have imagined the concept of a telescope, let alone the possibility of identifying a single star among billions and labeling it as the most mysterious object in the known universe. But we have, and it deserves that title. Every single time astronomers think they have figured it out, every time someone proposes a rational explanation and the community begins to relax, the star does something new, something unexpected, something that throws all the careful reasoning out the window and forces everyone back to the drawing board. Ask yourself this. If you were an alien civilization 1,000,000 years more advanced than we are, and you needed to harvest enormous amounts of energy from your star to power your world, what would you build? What kind of structure would you construct around your sun? And if a civilization on a distant planet happened to be watching your star with a telescope sensitive enough to detect the shadows of your construction, what would they see? This is not a fantasy question. This is the actual question that some of the most brilliant minds in astronomy began asking seriously in 2015, when a paper was published about this star that set the scientific world on fire. And before we go any further, before we trace the full arc of this extraordinary story from its beginnings to its most recent revelations, I want you to hold that question in your mind. Because everything that follows, every discovery, every theory, every twist and turn in this cosmic mystery, will eventually circle back to it. Let us begin at the beginning. The Kepler Space Telescope was one of the most ambitious scientific instruments ever launched into orbit. Before it was conceived, before a single engineer had drawn a single diagram, before a single dollar of funding had been allocated, the fundamental question it was designed to answer had already haunted astronomers for decades. Are there other planets out there? Not just in the abstract sense that we might reasonably assume the universe is too large and too old to have produced only one planetary system, but in the specific, measurable, scientifically verifiable sense. Are there worlds orbiting other stars? And if so, how many? How common are they? Could any of them support life? The method the telescope used to answer this question was elegant in its simplicity and staggering in its precision. When a planet orbits a star, and when that orbit happens to be aligned in such a way that the planet passes between the star and the observer, the planet blocks a tiny fraction of the star's light. From Earth's perspective, the star appears to dim ever so slightly for a brief period, then brighten again as the planet moves out of the way. This is called a transit. The dimming is usually tiny, a fraction of a percent, almost imperceptible. But Kepler was built to perceive it. It stared at a patch of sky containing over 150,000 stars simultaneously, measuring their brightness with extraordinary precision, watching for the telltale dips that would betray the presence of orbiting planets. The telescope was launched in March of 2009, and over the course of its nearly decade-long mission, it found thousands of exoplanets. It revolutionized our understanding of just how common planetary systems are. It confirmed that planets are not rare exceptions in the cosmos, but are, in fact, extraordinarily common. Almost every star, it turned out, had planets. The universe was lousy with worlds. But amid all this data, amid all those light curves and transit signals and confirmed planetary discoveries, there was one star whose data was so strange, so anomalous, so impossible to explain with any of the standard models, that it ended up changing the conversation entirely. Not just about planets, about everything. KIC 846-2852 was not discovered by a computer. It was not flagged by an automated algorithm. It was found by human eyes, by a small army of citizen scientists who were doing something genuinely remarkable with Kepler's data. In 2010, a project called Planet Hunters was launched through the Zooniverse platform, a public science initiative that allows ordinary people from around the world to participate in real scientific research. In the case of Planet Hunters, volunteers were shown actual light curve data from Kepler stars and asked to look for anything unusual, anything that might indicate the presence of a planet or any other interesting phenomenon. Trained algorithms were already doing this job, but the human brain has a peculiar talent for recognizing patterns that deviate from expectation, for noticing things that feel wrong without being able to immediately articulate why. The scientists behind Planet Hunters understood this, and they put it to use. And so it was that a group of citizen scientists, people who were not professional astronomers, who did not have advanced degrees in astrophysics, who were sitting at home on their computers in their spare time, were the ones who first noticed that this particular star was doing something deeply, fundamentally strange. The light curves from KIC 846-2852 showed dips. Not the clean, symmetrical, periodic dips you would expect from a transiting planet. These dips were chaotic. They were asymmetrical, meaning the brightness dropped differently on the way down than it recovered on the way up, which is not what you would expect from a solid, spherical object passing in front of a star. They were aperiodic, meaning they did not repeat on any regular schedule. And they were enormous. One of the dips blocked out as much as 22% of the star's total light. To put that in perspective, if Jupiter, the largest planet in our solar system, passed in front of our Sun, it would block roughly 1% of the Sun's light. Whatever was blocking KIC 846-2852's light was not a planet. It was something vastly, incomprehensibly larger. The citizen scientists who noticed this flagged it in the Planet Hunter system with the label interesting and bizarre. They called the star WTF star in their discussion forums, and the acronym was later cleaned up to stand for Where's the Flux? Though everyone knew what the original spirit of the label had been. They brought it to the attention of Tabitha Boyajian, a postdoctoral researcher at Yale University who was managing the Planet Hunters project. And when Boyajian looked at the data, her reaction was not the reaction of someone who had found a straightforward anomaly. It was the reaction of someone who had just seen something that made her question everything she thought she knew. She would later tell journalists that her initial response was essentially, "This is insane." And she meant it. Boyajian spent years analyzing the data, consulting with colleagues, ruling out one explanation after another. The dips could not be explained by instrumental error because they were too consistent and too large. They could not be explained by a group of planets because no group of planets could block 22% of a star's light. They could not be explained by a companion star because there was no evidence of one. They could not be explained by normal stellar activity, by sunspots or flares or pulsations, because the star was not that kind of star. KIC 846-2852 was a main sequence F-type star, slightly larger and hotter than our Sun, but fundamentally ordinary in every other way. It should not be dimming like this. Nothing about what it was doing made sense. In 2015, Boyajian and a large team of co-authors published a paper in the monthly notices of the Royal Astronomical Society. The paper was called Planet Hunters X, KIC 846-2852, Where's the Flux? And it laid out all the data in careful, rigorous detail, considered every mundane explanation they could think of, found each one inadequate, and ultimately concluded that the most likely explanation for the bizarre light curves was a swarm of comets. A family of fragmented comets, possibly disturbed by the gravitational influence of a nearby star, that had fallen toward KIC 846-2852 in an unusual formation, producing the complex, asymmetrical dimming patterns. It was a reasonable hypothesis. It was consistent with what we know about comets. It did not require anything exotic or unprecedented, and it was almost certainly wrong. But that would take time to prove, and in the meantime, the paper caught the attention of someone who was about to change the entire tenor of the conversation. Jason Wright is an astronomer at Penn State University. He is a serious scientist, a careful thinker, a person who is not given to wild speculation. He is also one of the world's leading experts on the search for extraterrestrial intelligence, or SETI, and specifically on the theoretical concept of Dyson spheres and other technological megastructures that a sufficiently advanced civilization might construct around their star. When Wright read Boyajian's paper, something clicked in his mind. Not because he thought aliens were the obvious answer, but because, as he would later explain, the scientific method demands that you consider all hypotheses, not just the comfortable ones. He reached out to Boyajian. He told her that he thought the anomalies in KIC 8462852's data were consistent with what you might expect to see if an alien civilization had constructed a massive structure, or series of structures, around their star. Something like a Dyson sphere, or what he preferred to call a swarm of megastructures. He wanted to add a brief mention of this possibility to the paper. Boyajian agreed, with a clear understanding that it would be presented as the least likely explanation, as the kind of hypothesis that you mention not because you believe it, but because intellectual honesty demands you acknowledge it. The result was a single paragraph at the end of the paper. A paragraph that said, in essence, we have considered every natural explanation we can think of and none of them is fully satisfactory. And while we do not believe this is the case, it is worth noting that the dimming patterns would be consistent with what one might expect to see if a large, irregularly shaped artificial structure were orbiting the star. That one paragraph detonated like a bomb. The media picked it up immediately. Headlines appeared around the world. Scientists baffled by strange star. Astronomers consider possibility of alien megastructure. Is this the first evidence of an extraterrestrial civilization? Within days, KIC 8462852 had acquired a new name. People started calling it Tabby's star, after Tabitha Boyajian, whose nickname was Tabby, and who now found herself at the center of one of the most remarkable scientific debates of the 21st century. The public response was extraordinary. People were fascinated, terrified, excited, skeptical, hopeful. Comment sections everywhere overflowed with theories and speculation. Religious communities weighed in. Conspiracy theorists found their moment. Scientists who had spent their careers maintaining professional detachment about the question of extraterrestrial life suddenly found themselves fielding questions from journalists, late-night television hosts, and their own families. The SETI Institute pointed their radio telescopes at the star to listen for any signals. They found nothing, but the act itself was significant. The scientific community was taking this seriously enough to actually look. But let us take a step back. Let us ask the question that forms the true backbone of this entire story. What exactly would an alien megastructure look like? Why would any civilization build one? And how would we know it if we found it? The theoretical foundation for this conversation was laid in 1960, not by a science fiction writer but by a physicist. Freeman Dyson was one of the most brilliant and unconventional scientific minds of the 20th century. He worked on the Manhattan Project as a young man, made fundamental contributions to quantum electrodynamics, proposed wild ideas like nuclear-powered spacecraft, and maintained throughout his long career a deep, serious interest in the question of how advanced civilizations might behave. In 1960, he published a paper in the journal Science titled Search for Artificial Stellar Sources of Infrared Radiation. The paper was short, barely more than a page, but its implications were enormous. Dyson's reasoning went something like this. Any technological civilization, if it survives long enough, will eventually face an energy crisis. Not the kind of energy crisis we are familiar with today, the depletion of fossil fuels, the limits of current technology, but a fundamental, civilizational scale energy crisis. As a civilization grows, as it expands its population and its technology, it requires more and more energy. And there is a hard limit to how much energy you can extract from your home planet. Eventually, a sufficiently advanced civilization would have to look to its star for energy. The star, after all, is the dominant source of energy in any planetary system, radiating power in all directions, most of it wasted into empty space. What if you could capture more of it? What if you could build a shell or a swarm of collectors around the star to intercept its energy output? This theoretical construct became known as a Dyson sphere, though Dyson himself preferred to call it a Dyson swarm, emphasizing that it would not necessarily be a solid shell, but rather a cloud of individual structures, satellites, collectors, habitats, that together would surround the star and harvest its energy. A Dyson sphere around our own sun would have a surface area approximately 550 million times greater than the surface area of Earth. It would be capable of capturing all of the sun's energy output, far more than we could ever need today, or in 1,000 years, or in 1,000,000 years. It would be the ultimate solution to an advanced civilization's energy needs. And here is the key insight that made Dyson's papers scientifically significant rather than purely speculative. A Dyson sphere would have an observable signature. If you wrapped a star in a shell of material, that shell would absorb the star's light and re-radiate it as heat, as infrared radiation. From outside, the star would appear dimmer in visible light and brighter in infrared. You could, in principle, search for this signature. You could scan the skies for stars that are anomalously dim in visible light but bright in infrared, and those would be candidates for Dyson sphere searches. Dyson's paper was not widely read for decades. It was considered too speculative, too far outside the mainstream of either physics or astronomy. But it never entirely disappeared. It influenced SETI researchers. It spawned a small but persistent literature of theoretical papers about megastructures. And when the data from KIC 846-2852 appeared, all of that theoretical groundwork suddenly became urgently relevant. Because here was a star that was dimming in ways no natural explanation could fully account for. Here was a star whose light curves were asymmetrical and complex in exactly the way you might expect if irregularly shaped, partially opaque structures were passing in front of it. Here was a star that had actually earned the right to make people say the words out loud. What if someone built something around it? Think about what that would mean. Not abstractly, not as a thought experiment, but as a literal, actual, physical reality. If the dimming of Tabby's star were caused by artificial structures, it would mean that at some point in the history of the universe, a civilization achieved a level of technological capability so far beyond our own that it makes our greatest engineering achievements look like children stacking blocks. The pyramids of Egypt, the Large Hadron Collider, the International Space Station, the entire global network of satellites and communications infrastructure we have built in the last century. All of it combined would not amount to a single component of whatever this civilization had constructed. We are talking about structures larger than planets, potentially larger than our entire solar system, engineered and deployed around a star. The sheer scale of it is almost impossible to hold in the human mind. And yet, here is something that Boyajian herself noted in interviews. The universe is 13.8 billion years old. Our civilization is, in cosmic terms, less than an eye blink old. We have had electricity for about 150 years. If there are civilizations out there that have been developing their technology for millions of years, or hundreds of millions of years, why would we assume that their capabilities are anywhere near our own? Why would we assume that what is impossible for us is impossible for them? This is the question at the heart of Tabby's star. And it is a question that refuses to go away even as scientists continue to search for natural explanations. But let us be honest. Let us be careful. Science is not served by wishful thinking, and the history of astronomy is full of anomalies that turned out, on closer inspection, to have perfectly mundane explanations. The history of SETI specifically is a long record of false alarms, of signals and phenomena that briefly looked promising and then turned out to be pulsars, or satellites, or terrestrial radio interference. The scientific community learned early to be rigorous about these things, to demand extraordinary evidence for extraordinary claims. So what are the natural explanations for Tabby's star? And why have they all, to varying degrees, fallen short? But let us take a step back. Let us ask the question that forms the true backbone of this entire story. What exactly would an alien megastructure look like? Why would any civilization build one? And how would we know it if we found it? The theoretical foundation for this conversation was laid in 1960, not by a science fiction writer but by a physicist. Freeman Dyson was one of the most brilliant and unconventional scientific minds of the 20th century. He worked on the Manhattan Project as a young man, made fundamental contributions to quantum electrodynamics, proposed wild ideas like nuclear-powered spacecraft, and maintained throughout his long career a deep, serious interest in the question of how advanced civilizations might behave. In 1960, he published a paper in the journal Science titled "Search for Artificial Stellar Sources of Infrared Radiation." The paper was short, barely more than a page, but its implications were enormous. Dyson's reasoning went something like this. Any technological civilization, if it survives long enough, will eventually face an energy crisis. Not the kind of energy crisis we are familiar with today, the depletion of fossil fuels, the limits of current technology, but a fundamental, civilizational scale energy crisis. As a civilization grows, as it expands its population and its technology, it requires more and more energy. And there is a hard limit to how much energy you can extract from your home planet. Eventually, a sufficiently advanced civilization would have to look to its star for energy. The star, after all, is the dominant source of energy in any planetary system, radiating power in all directions, most of it wasted into empty space. What if you could capture more of it? What if you could build a shell or a swarm of collectors around the star to intercept its energy output? This theoretical construct became known as a Dyson sphere, though Dyson himself preferred to call it a Dyson swarm, emphasizing that it would not necessarily be a solid shell but rather a cloud of individual structures, satellites, collectors, habitats, that together would surround the star and harvest its energy. A Dyson sphere around our own sun would have a surface area approximately 550 million times greater than the surface area of Earth. It would be capable of capturing all of the sun's energy output, far more than we could ever need today, or in 1,000 years, or in 1,000,000 years. It would be the ultimate solution to an advanced civilization's energy needs. And here is the key insight that made Dyson's paper scientifically significant rather than purely speculative. A Dyson sphere would have an observable signature. If you wrapped a star in a shell of material, that shell would absorb the star's light and re-radiate it as heat, as infrared radiation. From outside, the star would appear dimmer in visible light and brighter in infrared. You could, in principle, search for this signature. You could scan the skies for stars that are anomalously dim in visible light but bright in infrared, and those would be candidates for Dyson sphere searches. Dyson's paper was not widely read for decades. It was considered too speculative, too far outside the mainstream of either physics or astronomy. But it never entirely disappeared. It influenced SETI researchers. It spawned a small but persistent literature of theoretical papers about megastructures. And when the data from KIC 846-2852 appeared, all of that theoretical groundwork suddenly became urgently relevant. Because here was a star that was dimming in ways no natural explanation could fully account for. Here was a star whose light curves were asymmetrical and complex in exactly the way you might expect if irregularly shaped, partially opaque structures were passing in front of it. Here was a star that had actually earned the right to make people say the words out loud. What if someone built something around it? Think about what that would mean. Not abstractly, not as a thought experiment, but as a literal, actual, physical reality. If the dimming of Tabby's star were caused by artificial structures, it would mean that at some point in the history of the universe, a civilization achieved a level of technological capability so far beyond our own that it makes our greatest engineering achievements look like children stacking blocks. The pyramids of Egypt, the Large Hadron Collider, the International Space Station, the entire global network of satellites and communications infrastructure we have built in the last century. All of it combined would not amount to a single component of whatever this civilization had constructed. We are talking about structures larger than planets, potentially larger than our entire solar system, engineered and deployed around a star. The sheer scale of it is almost impossible to hold in the human mind. And yet, here is something that Boyajian herself noted in interviews. The universe is 13.8 billion years old. Our civilization is, in cosmic terms, less than an eye blink old. We have had electricity for about 150 years. If there are civilizations out there that have been developing their technology for millions of years, or hundreds of millions of years, why would we assume that their capabilities are anywhere near our own? Why would we assume that what is impossible for us is impossible for them? This is the question at the heart of Tabby's star. And it is a question that refuses to go away even as scientists continue to search for natural explanations. But let us be honest. Let us be careful. Science is not served by wishful thinking, and the history of astronomy is full of anomalies that turned out, on closer inspection, to have perfectly mundane explanations. The history of SETI specifically is a long record of false alarms, of signals and phenomena that briefly looked promising and then turned out to be pulsars, or satellites, or terrestrial radio interference. The scientific community learned early to be rigorous about these things, to demand extraordinary evidence for extraordinary claims. So what are the natural explanations for Tabby's star? And why have they all, to varying degrees, fallen short? Let us pause here and think about what this means on a human level. Imagine you are an astronomer. You have spent years training for this. You understand how stars work. You understand stellar physics, nuclear fusion, radiation pressure, stellar evolution. You have a comprehensive toolkit of knowledge and theory that allows you to look at any star, anywhere in the sky, and understand what you are seeing. And then this star comes along. And it does not fit. Not partially. Not approximately. Completely not. Every tool you reach for comes up empty. Every model you try fails. You are left staring at data that your entire professional life has not prepared you to understand. How do you sleep at night? How do you go back to the telescope the next day without feeling that the ground has shifted under you? Tabitha Boyajian has spoken publicly about this experience. She has said that the uncertainty, the not knowing, is both the most frustrating and the most exciting thing she has ever experienced in science. She describes the feeling of looking at the light curves and knowing that something unprecedented is happening, and not knowing whether the answer is mundane or world-changing. She has also been remarkable in her transparency about the process, setting up a Kickstarter campaign to fund additional observations of the star, raising over $100,000 from the public, people who were so fascinated by the mystery that they were willing to donate their own money to help solve it. The campaign was a symbol of something larger than itself. Tabby's star had captured the public imagination in a way that few scientific phenomena ever do. It was not just astronomers who wanted to know the answer. Millions of ordinary people around the world were following the story, refreshing news feeds, reading papers they only half understood, staying up late to watch live streams of telescope observations. The star had become, in some sense, a cultural phenomenon, a touchstone for all of humanity's deepest questions about its place in the universe. And then, in May of 2017, something extraordinary happened. The star started dimming again, in real time, while people were watching. Boyajian's team had set up a network of telescopes specifically to monitor the star, so that when a dimming event began, they could swing multiple instruments to observe it simultaneously across a range of wavelengths. And in May 2017, that network caught a dimming event in progress. Boyajian sent out an alert through Twitter, notifying the astronomical community that the star was actively dimming. Within hours, some of the world's most powerful telescopes were pointed at KIC 846-2852. What they found was extraordinary in its detail. The dimming event they observed was complex, unfolding over days, with multiple subdips and fluctuations. Different wavelengths of light were dimming by different amounts, and this wavelength dependence was one of the key pieces of data the community had been waiting for. Because if you know how much a light source dims at different wavelengths, you can deduce the size of the particles that are doing the blocking. Large, solid objects like planets or megastructures block all wavelengths equally. Fine dust particles, on the other hand, scatter shorter wavelength blue light more than longer wavelength red light, causing more dimming in the blue than in the red. The observations in 2017 showed wavelength-dependent dimming. The star was getting dimmer in blue light more than in red light. This meant that whatever was blocking the star's light was not a solid, opaque object. It was something like dust, composed of very fine particles, micron-sized grains or smaller. For many scientists, this was the result that finally tilted the balance toward a natural explanation. Fine dust could cause exactly this kind of wavelength-dependent dimming, and dust was a known, mundane component of stellar environments. Surely, this was the answer. Surely, the mystery was solved. Dust. But wait. If the answer were that simple, it would not still be keeping astronomers awake at night. The dust explanation has its own serious problems. First, you need a lot of it. To block the amounts of light observed during the major dipping events, you need an enormous quantity of dust. And dust, in a stellar environment, does not just hang around indefinitely. It is subject to radiation pressure from the star, which pushes it outward. It is subject to Poynting-Robertson drag, a relativistic effect that causes dust grains to slowly spiral inward toward the star and eventually be destroyed. It is subject to the star's gravity. Unless the dust is being continuously replenished from some source, it should dissipate relatively quickly. So where is it coming from? What is generating and maintaining this enormous quantity of fine dust? One proposal is that the dust is being generated by ongoing collisions in a debris disk, similar to the Kuiper belt in our solar system, but far more active and massive. Another is that it comes from one or more large bodies that are disintegrating as they orbit the star, perhaps comets or asteroids that are slowly being destroyed by the star's heat and gravity. These are plausible mechanisms, but none of them fully accounts for all the observed characteristics of the dimming. The extreme magnitude of the major events, the long-term secular dimming, the absence of the expected infrared excess. And there is something else. Something that has not received as much attention as it deserves. If the star has been dimming at Schaeffer's proposed rate of 20% over a century, and if this is caused by dust, then the amount of dust involved is truly staggering. You would need a quantity of material equivalent to multiple planetary masses of dust orbiting the star. Where does that much material come from? A single catastrophic event, like a large-scale planetary collision, could produce a lot of dust, but that dust would gradually spread, and over a century it would thin out rather than maintain a constant dimming effect. You would need a sustained, ongoing process of dust production at a truly extraordinary scale. Here is a theory, and it is important to emphasize that this is a theory, a speculative idea that has been proposed by some researchers. What if the answer to Tabby's star is not one thing but two things? What if there is a natural process responsible for part of what we observe, such as dust or cometary fragments, and simultaneously a separate, less natural process responsible for another part? This kind of composite explanation is not unprecedented in science. Many complex phenomena have multiple contributing causes, and the failure to find a single, complete natural explanation might simply mean that we need more than one. Of course, if you allow for composite explanations, the door to more exotic possibilities opens a little wider. Because one of the things that proponents of the megastructure hypothesis have pointed out is that a large, artificial structure, if it were associated with waste heat and material production, might also be surrounded by large quantities of dust. If an advanced civilization were constructing megastructures around their star, the construction process itself would generate debris, would scatter material, would create an environment in which both artificial structures and natural byproducts coexisted. The wavelength-dependent dimming you observe might be from the surrounding dust, while the large, dramatic dips might be from the structures themselves. This is speculation. This is not the mainstream scientific view. But it is a logical possibility that has not been definitively ruled out. And this is what makes Tabby's star so remarkable, so uniquely captivating in the history of astronomy. It is not just that we do not know the answer. It is that the range of possible answers spans the entirety of the imaginable universe, from the supremely mundane to the supremely extraordinary. And after years of intense study by some of the smartest people on Earth, we have not yet been able to pin the answer down. Let us talk about the scale of what we are dealing with when we discuss alien megastructures, because I think most people, even those who have followed this story, have not truly grappled with the implications. A Dyson sphere, in its most complete theoretical form, would be a rigid shell of material surrounding a star at roughly Earth-Sun distance, with the inner surface devoted to energy collection. The radius of such a structure, if built around a star like KIC 846-2852, which is slightly larger than our Sun, would be on the order of 200 million kilometers. The surface area would be, as we said, hundreds of millions of times greater than the surface of Earth. The material required to construct such a structure would have to come from somewhere. You would need to dismantle planets. You would need to strip mine moons and asteroids and the solid bodies of your entire planetary system, breaking them down into raw material and using it to build the shell. This would take an enormous amount of energy and time, and it would, in the process, eliminate the natural world that had previously existed in that system. A civilization that undertakes such a project has made a fundamental choice about its relationship with nature and with its home. It has decided that the needs of civilization, the need for energy, for space, for growth, outweigh the preservation of the natural planetary system. It is a choice that implies a level of technological capability, of organizational coordination, of long-term planning that is beyond anything our civilization has ever demonstrated. And here is the unsettling part. Here is the thing that should make you sit with this for a moment before moving on. We are, right now, in the early stages of an analogous process. We are building satellites. We are building solar collectors. We are discussing, at least theoretically, the possibility of large-scale space-based solar power generation. We are already transforming our planet's environment in service of our civilization's energy needs. The scale is incomparably smaller, but the trajectory, the direction of travel, points toward exactly the kind of civilization that would eventually build something like a Dyson sphere. If we survive, if we grow, if we continue to develop our technology. The physicist and futurist Nikolai Kardashev developed a classification system for civilizations based on their energy use. A Type 1 civilization uses the total energy available on its home planet. A Type 2 civilization harnesses the total energy output of its star. A Type 3 civilization uses the energy of its entire galaxy. We are currently, by Kardashev's definition, somewhere around 0.73 on the scale, meaning we use a significant fraction of Earth's available energy but have not yet mastered our planet's full potential. A civilization building a Dyson sphere is, by definition, a Type 2 civilization. And the gap between where we are and a Type 2 civilization is so vast that it is almost incomprehensible. But here is what is important to understand. In a universe 13.8 billion years old, civilizations like ours, young, technologically naive, just beginning to peer out into the cosmos, are not necessarily the rule. We might be early. We might be extraordinarily early, cosmically speaking. If even a small fraction of the civilizations that have ever arisen in the Milky Way have survived to reach the Type 2 stage, there could be dozens or hundreds of Dyson spheres in our galaxy right now. And if we could detect even one of them, the implications for our understanding of our place in the universe would be revolutionary in a way that no other discovery in history could match. This is why Tabby's star matters so much. Not because we think it is probably an alien megastructure, but because it is the most promising candidate we have ever found for testing whether such things exist at all. Let us now turn to the specific observations that followed the 2017 dimming events, because the scientific work done in that period represents some of the most careful and sophisticated astronomy ever applied to this problem. The 2017 dimming events, which were given names by the observing team, including Elsie, Celeste, Scarabray, and Anchor, were observed with a remarkable array of telescopes. Ground-based observatories in multiple countries participated. The Swift Space Telescope, which is normally used to study gamma-ray bursts, was pointed at the star. The Hubble Space Telescope observed it in ultraviolet light. A network of amateur astronomers with modest equipment contributed photometric data. It was an extraordinary cooperative effort, driven in part by the Kickstarter-funded observing campaign that Boyajian had organized. The multi-wavelength data from these events were rich and complex. They confirmed the wavelength-dependent dimming, meaning dust-like particles were involved. They showed that the dimming events were not all identical, that each one had a slightly different profile and depth, suggesting that the obscuring material was not homogeneous but varied in composition and density from event to event. They showed that the events were not periodic, that they did not repeat on a regular schedule that would be expected from material in a simple circular orbit. And here is something that has been largely overlooked in the popular accounts of this story. Some of the 2017 events showed what appeared to be multiple distinct components, as if the blocking material were not a single cloud but several distinct structures or clumps at slightly different positions. The complexity of the dimming profiles was, in the words of some researchers, reminiscent of a city, of something highly structured, something composed of many individual parts rather than a single amorphous cloud. Now, this observation has to be treated with caution. Complexity in astronomical data can arise from many natural causes. A fragmented comet, for example, would produce multiple distinct clumps. An irregular debris cloud would be inhomogeneous. Pattern recognition in the human brain, especially when primed by expectation, is notoriously unreliable. Scientists know this. They try to account for it. But the observation is there in the data, and it deserves to be mentioned. In 2018, Boyajian and her team published a major paper analyzing the 2017 events in detail. The conclusion was careful and measured. Fine dust was the most likely cause of the dimming, but the source of the dust remained unexplained. The paper acknowledged that the complete picture of the star's behavior, including the long-term secular dimming, the dramatic short-term dips, and the wavelength-dependent characteristics, did not fit neatly into any single well-understood scenario. The mystery, in other words, was not solved. It was better characterized, more precisely defined, but not solved. Around this same time, another line of investigation was producing interesting results. Astronomers were looking at the infrared properties of KIC 846-2852 in more detail. If the star were surrounded by a large amount of warm dust, this dust would radiate heat and produce an infrared excess above what the bare star would generate. Earlier studies had found no significant infrared excess, which was one of the arguments against the dust hypothesis. But more careful analyses with different infrared telescopes and at different wavelengths were painting a more nuanced picture. Some studies found evidence of a modest infrared excess, consistent with a small amount of warm dust very close to the star. But the excess was far too small to account for the amount of dust needed to cause the major dimming events. This created a paradox. You needed a lot of dust to explain the dimming, but you were not finding the infrared emission that a lot of dust would produce. Where was the missing heat? There are a few possible explanations. One is that the dust is very cold, meaning it is far from the star, and its thermal emission is at wavelengths that have not been well observed. Another is that the dust is structured in a very specific geometry that happens to minimize its infrared emission in the direction of Earth. Another is that the dust is very dark, absorbing radiation efficiently but not re-radiating it at the wavelengths expected. And another, more exotic possibility is that whatever is absorbing the star's light is not simply re-radiating it as heat but is somehow using it, converting it. This is, of course, exactly what a solar energy harvesting megastructure would do. This last possibility is not mainstream science. It is speculation. But it is the kind of speculation that responsible scientists do allow themselves to articulate, because ruling things out is as important as proposing things, and you cannot rule something out if you refuse to name it. Now let us step back even further and think about the broader context in which Tabby's star sits. Because the story of this star is not just a story about one anomalous object in space. It is a story about how we search for signs of other civilizations, about the limits of our imagination, and about the profound difficulty of recognizing something fundamentally alien. The search for extraterrestrial intelligence has a long and complicated history. Since the early 1960s, when Frank Drake pointed a radio telescope at two nearby stars and listened for signals, SETI has been a legitimate, if often underfunded branch of scientific inquiry. The premise of most SETI efforts is that an advanced civilization wanting to communicate would broadcast radio or optical signals. We would recognize a signal by its regularity, by its complexity, by the presence of mathematical patterns or other characteristics that could not be produced naturally. We would receive it, decode it, and know that we had made contact. But this premise rests on a significant assumption, that an alien civilization would want to communicate with us, would be broadcasting in our direction at the right wavelengths, and would be doing so on a timescale that overlaps with the period in which we are listening. The galaxy is 100,000 light-years across. Even if there are thousands of civilizations in it, the probability that any of them is specifically broadcasting toward Earth right now is small. The so-called Great Silence, the fact that we have heard nothing, does not necessarily mean there is no one out there. It might simply mean that we are looking in the wrong way. This is why the concept of techno-signatures has gained increasing prominence in the SETI community. Rather than searching for deliberate communications, why not search for the physical evidence of advanced technology? Stars with unusual dimming patterns. Infrared sources with properties inconsistent with natural objects. Unexplained megastructure signatures. Even the presence of certain atmospheric gases on distant planets that could only be produced by industrial activity. These techno-signatures would not require any deliberate act of communication from the alien civilization. They would simply be the observable consequences of a technological civilization going about its business. Tabby's star, in this framework, is the most interesting techno-signature candidate we have ever found. Not because we think it is definitely artificial, but because it fits, in some ways, the profile of what an advanced civilization's infrastructure might look like, and because no fully satisfying natural explanation has yet emerged. The concept of an advanced civilization not communicating, not trying to reach out to us, but simply existing and being observable through its industrial output, is both exciting and eerie. Think about what it would mean from our perspective if we discovered that another star's behavior was best explained by the presence of a Dyson sphere. We would not be receiving a message. We would not be in contact. We would simply be observing, watching, like someone on the ground watching airplane contrails in the sky without being able to communicate with the pilot. We would know they were there. We would not know anything about them. We would not be able to speak to them. They might not even know we exist. And from their perspective, if they were even aware of us, they might see us the same way. Tiny, distant, primitive creatures on a small world, barely able to venture beyond our own atmosphere, watching their star with our primitive instruments and wondering what they are. The psychological impact of such a discovery would be staggering, not just for scientists, not just for governments and religious institutions and philosophers, though all of those would be profoundly affected, but for every human being. For every person who has ever looked up at the night sky and wondered. For every child who has ever asked, "Are we alone?" The answer would arrive not as a voice, not as a message, not as a landing, but as a shadow, as a dip in a star's light curve, as a line of data on an astronomer's screen. Consider what it means to be the person who identifies that shadow, to be the astronomer who can say, with confidence, that what we are seeing cannot be explained by any natural process we know of, that the most parsimonious explanation is that someone built something around that star. The responsibility of that claim is almost incomprehensible. it would be the most important discovery in human history. It would be a discovery that would immediately call into question everything, not just our science and our technology, but our sense of who we are in the cosmos. Our place. Our significance. This is why scientists are so careful. This is why they keep proposing natural explanations and testing them and refining them, even when the data continues to resist. Because the alternative, the truly extraordinary alternative, demands truly extraordinary proof. And we are not yet there. But we are also not nowhere. The mystery is real. The data is real. And the investigation continues. Let us now talk about some of the most recent work done on the star, because the story has not ended, not by a long way. In the years since the 2017 observing campaign, astronomers have continued to monitor KIC 846, 2852 and have added new dimensions to the puzzle. One of the most intriguing recent developments involves the periodicity of the dimming events, or rather, the apparent lack of it. When you have a large body orbiting a star and periodically blocking its light, you expect to see a pattern. The orbital period, the time it takes for the body to complete one orbit, creates a repeating cycle of transits. Even if the body is irregular in shape, producing asymmetrical dimming profiles, the repetition itself would be periodic. But the dimming events of Tabby's star have stubbornly refused to repeat on any obvious schedule. Some researchers have suggested that there may be a long-period quasi-periodicity lurking in the data, a cycle of roughly 800 days or so, that could explain some of the major dipping events as recurring transits of a large body or swarm of bodies in a roughly 2.2-year orbit. This is an attractive idea because it would connect the sporadic, apparently random dips into a coherent physical picture. If confirmed, it would support a model in which a large, structured cloud of material, whether natural or artificial, is in a specific orbit around the star and transits in front of it roughly every 800 days. But the evidence for this periodicity is tentative. The pattern fits some of the major events, but not all of them. And with a data set that covers only about 4 years of intensive monitoring, it is difficult to confirm a periodicity of 2 years with confidence. More observations over a longer baseline are needed. Another fascinating thread of research involves the spectroscopic study of Tabby's star. Spectroscopy is the analysis of a star's light by splitting it into its component wavelengths, creating a spectrum that reveals information about the star's chemical composition, temperature, velocity, and other properties. When you look at a star's spectrum, you see a rainbow of colors crossed by dark lines called absorption lines. These lines are produced when atoms in the star's atmosphere absorb light at specific wavelengths. The pattern of these lines is unique to each type of atom, like a fingerprint, and astronomers can use them to identify what elements are present and in what quantities. Spectroscopic observations of KIC 846, 2852 have revealed something that has not received as much attention as it deserves. During dimming events, the star's spectrum changes. Specifically, certain absorption lines become more prominent or shift slightly, suggesting that material is moving between the star and the observer and imprinting its own absorption signature on the star's light. This material has a composition that can be analyzed. And what the spectroscopic data suggests is that the material contains calcium, specifically ionized calcium. Calcium is a common element in astronomical contexts. It is found in comets, in asteroids, in protoplanetary disks. The presence of calcium in the absorbing material is, in principle, consistent with a natural origin. But it is also consistent with other things. Calcium is a major component of many silicate minerals, the stuff that planets are made of. If something large and rocky, something planetary in scale, were being disrupted in the vicinity of KIC 846-2852, it might release large amounts of calcium-bearing material into the surrounding space. What might disrupt a planet? A catastrophic collision with another large body. A tidal disruption event, where a planet passes too close to a massive object and is torn apart by gravitational forces. Or, in the more speculative domain, the deliberate dismantling of a planetary body to harvest its material for construction. This last idea, once again, is not mainstream science. It is the kind of speculation that is carefully bracketed and labeled as such by responsible researchers. But it is worth understanding that in the context of megastructure construction, the dismantling of planetary bodies is not just a theoretical possibility. It is a necessary step. If you are building a Dyson sphere, you need raw material. The most readily available raw material is the planets and smaller bodies of your own stellar system. You would have to take them apart. And taking apart a rocky planet would release enormous quantities of rocky debris, including calcium-bearing silicates. The spectroscopic signature of such a process might look exactly like what we are observing. Again, this is speculation. But it is informed speculation, grounded in physical reasoning. Let us now consider what has been happening with SETI efforts aimed at this star. Shortly after the original paper was published in 2015, the SETI Institute used the Allen Telescope Array, a network of radio telescopes in California dedicated to SETI research, to observe KIC 846-2852. They listened for radio signals across a wide range of frequencies, from about 1 to 10 gigahertz, looking for anything that might indicate artificial transmission. They also looked for brief, intense laser pulses that might indicate optical communication. They found nothing. No signals. No pulses. No evidence of deliberate communication. This result was widely interpreted as reducing the probability that the star hosts an alien civilization. And that interpretation is understandable. If you were a Type 2 civilization capable of building megastructures around your star, you might also be broadcasting radio or laser signals. But you might not. You might have no interest in communicating with primitive civilizations 1,000 light years away. You might communicate through means we have not imagined. You might have moved beyond communication technologies that use electromagnetic radiation entirely. The absence of a signal, in this context, is suggestive but not conclusive. More recently, researchers have used other methods to look for technological signatures around KIC 846-2852. One approach involves looking for signs of laser communication. Unlike radio waves, which spread out in all directions and become very dilute over large distances, laser signals can be extremely focused and intense. But they are also directional, meaning you have to be in the right place to detect them. Various groups have searched for optical laser pulses from the direction of the star without finding any convincing candidates. Another approach looks for excess heat radiation in the far infrared, specifically the kind of emission you would expect from a structure or swarm of structures at a specific temperature. This is essentially a search for the waste heat of a technological civilization. All machines generate waste heat. A civilization that is harnessing the energy of its star and using that energy for computation, for manufacturing, for life, would release that energy as heat. The heat would radiate into space at a specific temperature, depending on the size and structure of the civilization's infrastructure. Searches of this type, using data from infrared space telescopes, have not yet found clear evidence of such emission from KIC 846-2852. But the limits of these searches are such that they could not detect a megastructure that was less than a certain fraction of the star's total luminosity, and a partial, incomplete Dyson sphere might well fall below those detection thresholds. The search continues, and with each new generation of telescopes, the sensitivity of these searches improves. The James Webb Space Telescope, launched in December 2021, is the most powerful space telescope ever built. Its infrared capabilities are orders of magnitude more sensitive than those of its predecessors. It can observe the detailed infrared spectra of distant objects with unprecedented precision. And while it has not yet been used for a dedicated study of KIC 846-2852, the potential is there. If there is a megastructure around that star, James Webb might be able to detect its infrared signature to see the heat that all that harvested energy eventually becomes. Think about what that would mean. The James Webb Telescope, floating in space 1,000,000 miles from Earth, aimed at a point of light 1,400 light-years away, detecting the heat signature of an alien civilization's energy infrastructure. The data would arrive in the form of a graph, a spectrum with a characteristic shape. It would not look dramatic. It would not announce itself. It would be a faint, subtle excess of radiation at specific infrared wavelengths. But if the analysis were correct, if the interpretation held up under scrutiny, it would be the moment. The moment everything changed. We have not yet had that moment, but we are closer to having the tools to either find it or rule it out than we have ever been. Now, I want to take a different angle on this story. I want to talk about what the existence of Tabby's star tells us about ourselves, about our scientific process, our cultural anxieties, our deepest hopes and fears. When the story of this star first broke into public consciousness in 2015, the response was remarkable in its emotional intensity. It was not just curiosity. People were genuinely moved, excited in a way that most scientific discoveries do not produce, and anxious in a way that is equally revealing. The excitement is easy to understand. The possibility that we had found evidence of extraterrestrial intelligence, even the remote, uncertain, carefully hedged possibility, touches something very deep in the human psyche. We are a species that has spent its entire existence looking at the sky and wondering. We have told stories about the gods who live above the clouds, the lights that move differently from the stars, the cosmic order in which we play some role. The question of whether we are alone in the universe is, in some sense, the oldest question we have ever asked. And to come closer to an answer, to have a specific star, a specific set of coordinates, a specific data set that might bear on that question, is not just scientifically interesting. It is mythologically significant. But the anxiety is equally revealing. Because alongside the excitement, there was also fear. Fear of the implications. Fear of what it would mean if we were not alone. Fear, strangely, of contact, of being seen, of what an advanced civilization might do to a primitive one. History on Earth is not encouraging in this regard. Every time a more technologically advanced civilization has encountered a less advanced one, the results for the less advanced civilization have been catastrophic. Colonization, exploitation, cultural annihilation. The pattern is repeated so often and so consistently in human history that it is hard not to apply it as a template to the cosmic scale. Stephen Hawking, before his death in 2018, explicitly warned against attempts to actively communicate with extraterrestrial civilizations. He argued that announcing our presence to an advanced alien civilization would be analogous to the Native Americans encountering Columbus. Extremely dangerous for the weaker party. He recommended listening, not broadcasting, observing, not revealing ourselves. But here is the uncomfortable truth. It may already be too late for that. Our radio and television signals have been leaking into space for over a century. The wavefront of our electromagnetic emissions, an expanding bubble of I Love Lucy and Hitler speeches and Apollo mission broadcasts and satellite communications, has already traveled more than 100 light-years from Earth. Any civilization within that bubble that has sufficiently sensitive instruments already knows we are here. And 100 light-years is a significant volume of space containing numerous stars and potentially hundreds of planetary systems. Moreover, the question of whether discovering Tabby's star as a megastructure would be dangerous for us specifically is more nuanced than the Columbus analogy suggests. KIC 846-2852 is 1,400 light-years away. Any communication between us and a civilization there would take 1,400 years for the message to arrive. And if they sent a response, we would not receive it for another 1,400 years. So any meaningful interaction is on a timescale of millennia. The scenario of a fleet of alien ships arriving at Earth in response to our detection of their megastructure is not realistic on any near-term human timescale. The discovery would not put us in immediate danger. What it would do is fundamentally change our self-perception, our sense of uniqueness, our place in the cosmic order. And that transformation of self-perception might be the most profound and disorienting thing that has ever happened to our species. Consider the Copernican revolution. Before Copernicus, the dominant worldview held that Earth was the center of the universe, that the sun and the planets and the stars all revolved around us, that we were the special purpose of creation. When Copernicus proposed, and Galileo confirmed, that Earth was just one planet among several orbiting a somewhat ordinary star, the impact was enormous. Not just scientific, cultural, philosophical, religious. It took centuries for human thought to fully absorb and integrate this change. We still have not fully done so, in some respects. The discovery of Tabby's star as a megastructure would be a Copernican revolution of a completely different order. It would not just remove us from the center of the solar system. It would place us in a universe populated by vastly superior intelligences. Intelligences so far beyond us that their infrastructure alone dwarfs anything we have ever built or imagined building. It would raise questions that no existing human institution, scientific, religious, political, or philosophical, is prepared to answer. What do we do? What do we say? What do we become in light of this knowledge? These questions are not idle speculation. They are actively being discussed by scholars across multiple disciplines. Theologians have been grappling with the implications of extraterrestrial intelligence for decades. The Vatican, to its credit, has been relatively open about this, with Vatican astronomers and philosophers discussing how the discovery of intelligent life elsewhere would or would not contradict core tenets of Christian theology. Other religious traditions have their own frameworks for addressing the question. The philosophical literature on the ethics of contact, the question of whether and how to communicate, the rights and moral status of non-human intelligent beings, has been growing steadily for years. Governments have drafted preliminary plans, some of them publicly available, some not, for how to handle the announcement of confirmed contact. All of this preparation, all of this thinking, exists in a kind of anticipatory mode. We are preparing for something we do not know will ever happen. But Tabby's star is the first piece of physical, observational evidence that has made that preparation feel less like science fiction and more like urgent, practical necessity. Now, I want to spend some time on a dimension of this story that is often overlooked in the breathless coverage of the megastructure hypothesis. The very human drama of doing science in the public eye. Because the story of Tabby's star is not just a story about a mysterious star. It is also a story about scientists navigating the intersection of rigorous inquiry and public expectation. And that story is, in its own way, as remarkable as anything else we have discussed. When Tabitha Boyajian published her paper in 2015, she had no idea what was about to happen. She was a postdoctoral researcher, a young scientist early in her career, doing careful, methodical work on an anomalous dataset. The paper she published was appropriately cautious, appropriately hedged, full of the qualifications and caveats that responsible science requires. And then the media got hold of it, stripped away most of the qualifications, and ran headlines that were, to put it mildly, more dramatic than the paper itself. Boyajian found herself overnight in the position of spokesperson for the most extraordinary scientific mystery in years, possibly decades, possibly ever. She was not the author of the megastructure hypothesis. Jason Wright was. But because her name was on the paper, because the star bore her nickname, she became the face of the story. She was invited onto television programs, interviewed by science journalists and non-science journalists, asked to explain not just the data but what she personally believed about extraterrestrial civilizations, about the likelihood of alien intelligence, about the future of humanity. She handled it with remarkable grace. She consistently maintained that the megastructure hypothesis was the least likely explanation she and her team had considered. She consistently said that she expected a natural explanation to emerge. She consistently refused to endorse speculation beyond what the data supported. And she consistently, throughout all of it, communicated genuine excitement and wonder about the mystery itself, without overstating what was known. This is harder than it sounds. In a media environment that rewards certainty and drama over nuance and qualification, a scientist who refuses to say, "Yes, this is probably aliens," is often portrayed as evasive or boring. The public, understandably, wants an answer. They want to know. And the correct scientific response, "We don't know yet, and here are the various possibilities being considered," is deeply unsatisfying to anyone who has been primed by headlines to expect a revelation. Jason Wright navigated a similar challenge from a slightly different direction. He was explicitly an expert in the field of technosignatures and alien megastructures, which meant that when the media wanted someone to say the exciting things, they came to him. And he was, to his credit, both willing to engage with the exciting possibilities and rigorous about the standards of evidence required to actually embrace them. He wrote extensively on his blog and in scientific papers about the precise meaning of the megastructure hypothesis, what evidence would be needed to support it, what evidence would refute it, and why it was scientifically legitimate to include it as a hypothesis even if it was unlikely. His engagement with a public debate around Tabby's star helped elevate the broader conversation about technosignatures from the fringes of scientific acceptability to the mainstream. The search for technosignatures, including potential megastructures, is now explicitly endorsed by NASA and included in the National Academy's decadal surveys of astronomy priorities. That shift is, in part, a consequence of the conversation that Tabby's star forced. There is something deeply admirable about the way the scientific community handled this episode. Not perfectly, not without mistakes, not without occasional lapses into speculation that went beyond the data. But overall, the scientific process worked as it should. A genuine anomaly was identified and published. Multiple competing hypotheses were proposed and tested. New observations were gathered and analyzed. The community remained engaged and skeptical and curious in equal measure. And through all of it, the data accumulated, the understanding deepened, and the mystery continued to reveal new facets even as some old questions were partially answered. Let us now explore some of the more exotic theoretical territory around the star, the places where imagination and physics meet and where the most interesting speculative ideas live. One concept that has been proposed in the context of Tabby's star is that of a stellar engine. A stellar engine is a theoretical megastructure that not only harvests a star's energy but actually uses it to propel the star through space. The idea is based on the fact that a star radiates energy in all directions, and if you could somehow focus or redirect that radiation asymmetrically, reflecting more in one direction than another, the resulting net radiation pressure would act as a kind of rocket, slowly accelerating the star in the opposite direction. Why would anyone want to move a star? One reason is survival. In the very long run, the galaxy is a dangerous place. Stars sometimes collide. Galaxies merge. Gamma-ray bursts from distant events can sterilize vast regions of space. A sufficiently advanced civilization, thinking on billion-year timescales, might want the option to relocate their star, to move it away from danger or towards some other destination. A civilization that has mastered the technology to build a Dyson sphere might not consider moving their star a particularly exotic next step. The specific stellar engine concept that could produce observable signatures is called a Shkadov thruster, named after the Russian astrophysicist Leonid Shkadov, who proposed it in 1987. It consists of a large, fixed mirror placed on one side of the star, positioned such that it reflects a portion of the star's light back toward the star and focuses it in a specific direction. The asymmetric radiation pressure would create a slow but steady thrust. Over millions of years, this could accelerate the star to a significant fraction of its natural velocity relative to the galactic center. From outside the system, you would observe a star with an asymmetric optical environment, emitting more light in some directions than others, and possibly with a complex pattern of dim regions as the mirror and its supports periodically transit across the star's face. Would this look like Tabby's star? In some respects, possibly. In others, no. The Shkadov thruster model does not predict the specific patterns of variability observed. But it is an example of how the theoretical space around megastructures is genuinely rich, full of ideas that have been worked out in enough detail to make specific predictions, and how some of those predictions are at least broadly consistent with some of what we observe. Another speculative territory involves the idea that the star's long-term secular dimming, if real, could be evidence of progressive construction. If a civilization were in the process of building a Dyson sphere around their star, the construction would proceed incrementally. Each new component added would block a little more of the star's light. Over decades or centuries, the total blocked light fraction would increase. The result would be exactly what Schaefer claimed to have found: a steady, progressive decrease in the star's measured brightness over a century or more. This idea is elegant in its simplicity. If you are seeing a star get slowly dimmer over decades, and if you are simultaneously seeing dramatic, complex, irregular dimming events, and if no natural explanation fully accounts for either, the possibility that you are watching a civilization in the process of building something is at least logically consistent with the observations. It does not prove anything, but it fits. The emotional weight of this idea is considerable. Think about what it would mean to be watching, right now, in real time, the construction of the largest engineering project in the history of another civilization. The light that left that star in the year 600 CE is arriving at Earth right now, and that light has been modified by whatever is happening there. The photons that hit our detectors today left their star around the time that Muhammad was born, that Justinian was ruling the Byzantine Empire, that the Tang dynasty was beginning its golden age in China. Whatever is happening at KIC 846-2852, whatever is casting those shadows, has been going on for at least that long. And whatever state the construction is in now, in 2024, we will not see it for another 1,400 years. There is a kind of melancholy in this that is hard to articulate. We are, by necessity, historians of another civilization's sky. Whatever we observe is ancient news. Events finished 1,400 years before we learn of them. If the megastructure hypothesis were true, the civilization doing the building would by now, in their present, have completed far more of their work, or perhaps completed it entirely, or perhaps even moved on to something new. We are seeing a snapshot of their deep past. A photograph of their civilization taken 14 centuries before our telescopes even existed. And they, if they have the equivalent of our technology, cannot see us at all yet. Our earliest radio signals, the leakage from the first radio transmitters in the early 20th century, will not reach the location of KIC 846-2852 for another 13 centuries. We are communicating across time as much as across space. Now let us ask a different kind of question. Not what might be causing the dimming, but what it would mean, scientifically and philosophically, if we definitively ruled out alien megastructures. Suppose in the next few years, more detailed observations with more powerful telescopes produced a perfectly satisfying natural explanation for all of KIC 846-2852's anomalies. Suppose someone found a new class of cometary behavior, or a novel type of stellar variability, or an unusual disk configuration that fit every piece of data. The mystery would be solved. The alien megastructure hypothesis would be ruled out for this specific star. Would that be a disappointment? In one sense, yes. The hope of having found evidence of another civilization would be extinguished. But in another sense, the discovery of a new natural phenomenon, something genuinely unprecedented in stellar physics, would be extraordinarily valuable in its own right. Science advances as much through anomalies as through confirmations. The anomaly of Tabby's star has already driven years of new observations, new analyses, new theoretical work, new instruments, and new thinking about how we search for both natural and artificial phenomena in the cosmos. Whatever the answer turns out to be, the question has been worth asking. And if the natural explanation that emerges requires a truly exotic or unprecedented physical scenario, something we have never seen before, something that stretches the known boundaries of stellar physics, then in a sense we are still making a remarkable discovery about the universe, just a discovery about its natural complexity rather than its civilizational diversity. Some scientists have argued that the very robustness of the mystery, the fact that so many careful thinkers with so many tools have been unable to find a fully satisfying natural explanation, is itself significant. It does not prove that the explanation is unnatural, but it does suggest that, whatever the answer is, it is not going to be trivial or obvious. Something genuinely unusual is happening around KIC 846-2852. Whether that unusual thing is a new astrophysical phenomenon or evidence of alien technology, and that in itself is a statement worth making. Think about this from a historical perspective. The history of astronomy is full of moments when an anomalous observation turned out to reveal something profound about the universe. Pulsars were initially so strange and so regular that the astronomers who discovered them jokingly labeled the first one LGM-1 for little green men, before the natural explanation of rapidly rotating neutron stars was found. Quasars were so luminous and compact that astronomers initially struggled to believe they were real, before the mechanism of supermassive black holes accreting matter was understood. Dark matter was proposed to explain gravitational anomalies in galaxy clusters that made no sense under conventional gravity, and while its nature remains unknown, its existence is now firmly established. Each of these anomalies, when initially encountered, looked like a mystery that might require something revolutionary. And in each case, they did require something revolutionary. Just usually a revolutionary new natural phenomenon rather than a revolutionary revision of basic physics. Tabby's star is in this tradition. Whatever it turns out to be, it has already forced us to think harder, look more carefully, and expand the range of phenomena we consider possible. That is the highest service a scientific mystery can perform. Now let us talk about some of the more recent proposals for what might be causing the behavior of the star, because the scientific literature has continued to generate new ideas even as the observational campaign has matured. One of the most interesting recent proposals involves interstellar material. Not material orbiting the star itself, but material in the interstellar medium through which the star is moving. As stars move through the galaxy, they plow through the thin, diffuse gas and dust that fills interstellar space. Usually this material is too thin and too uniform to produce any noticeable effect on our observations. But if KIC 846-2852 happen to be passing through or near a denser-than-average region of the interstellar medium, perhaps a molecular cloud or a region recently disturbed by a supernova, the accumulated absorption from that material might contribute to both the long-term dimming and some of the shorter-term variability. This idea has not gained wide acceptance, partly because the interstellar medium is generally too thin and too smooth to produce the sharp, complex, variable dimming profiles observed. But it serves as a reminder that the list of candidate explanations is not yet exhausted, that creative thinking about the physics of the galactic environment continues to generate new possibilities. Another proposal involves the concept of a tidally disrupted body. If a large body, a planet or a very large comet, were to pass too close to the star and be disrupted by its gravity, it could produce a stream of material spread along the orbital path. As this stream of material precesses and evolves, different parts of it would transit the star at different times, producing complex, variable dimming events. Over longer timescales, the material would gradually disperse, causing a slow decrease in the depth and frequency of the dimming events. This model makes some specific predictions about the time evolution of the dipping behavior that can be compared with observations. Some researchers have found encouraging agreement between this model and parts of the observed data. Others have pointed out discrepancies. As with so many proposed explanations for this star, it does some of the work but not all of it. There is also a body of literature exploring whether the behavior of Tabby's star might be related to intrinsic stellar variability in ways we have not fully characterized. F-type stars, the class to which KIC 846-2852 belongs, can have complex convective zones and magnetic activity cycles. While the star does not show the classic signs of a strongly magnetically active star, there may be subtle stellar phenomena at play that interact with circumstellar material to produce the observed dimming patterns. The coupling between stellar activity and the behavior of surrounding material is an area of active research, and it is possible that Tabby's star represents an extreme example of such coupling. One more idea deserves mention, not because it is particularly well supported, but because it is genuinely creative and reflects the spirit of open inquiry that this star demands. Some researchers have speculated about the possibility that the star is surrounded by a very large, very cold, very dark structure that is nearly invisible to most of our telescopes. A structure that is not a Dyson sphere in the classic sense, but something more like a dark halo of material, perhaps a collection of very dark, cold bodies too faint to detect individually, but capable of collectively blocking significant amounts of the star's light. This idea has been explored in the context of so-called Dyson dots, small, very dark objects placed in specific orbits to create a controllable sunshade. If you wanted to fine-tune the energy output reaching a planet, or to create shadow patterns for some other purpose, you might deploy a large number of small, very dark objects distributed around your star. The aggregate effect would be dimming, variable as the distribution of objects changed, and the individual objects would be too small and too dark to detect directly. Once again, this is speculative territory. But it is speculative territory that is consistent with known physics and that makes specific observational predictions. The darkness of the proposed objects would mean they absorb rather than scatter light, reducing the infrared excess. Their small size would produce wavelength-independent dimming within each object, but their variable distribution would produce overall variability in the aggregate dimming. The picture is complicated, but it is not incoherent. Now let us take a step into the territory of what this star means for our understanding of the Fermi paradox. The Fermi paradox, named after the physicist Enrico Fermi who posed the essential question in 1950, is simple to state and extraordinarily difficult to answer. Given the age of the universe, given the vast number of stars and planets, given the wide range of environments conducive to life, and given the plausibility of at least some of those environments developing intelligent life, where is everybody? Why has our galaxy not been colonized? Why are we not picking up signals? Why do we see no evidence, anywhere in the sky, of alien civilization? Various solutions to the Fermi paradox have been proposed over the decades. The Great Filter hypothesis suggests that there is some step in the development from simple life to spacefaring civilization that is extraordinarily difficult to pass through, and that most species fail at that step. If the Great Filter lies in our past, we might be very rare, one of the few species to have made it this far, and the future might be open. If the filter lies in our future, almost every civilization that reaches our current level eventually fails, and we should be very worried about our own prospects. Another class of solutions suggests that advanced civilizations exist but are simply not engaging with us, either because they have no interest, because they are aware of us and have decided to leave us alone in a kind of cosmic nature reserve, or because they have transcended the kind of electromagnetic communication we are looking for and are doing something else entirely. Tabby's star potentially bears on this debate in an interesting way. If the dimming is caused by a Dyson sphere, it would represent the first example of what might be called a passive technosignature, evidence of alien civilization that was not intended as a signal but was simply the byproduct of their technology. And if we can find one example of such a technosignature, it suggests that passive signatures may be detectable, and that the reason we have not found them previously is not that they do not exist, but that we have not had the instruments or the methods to find them until now. This would be a partial resolution of the Fermi paradox, not a complete one. We would still not know why these civilizations are not communicating with us, or why they have not colonized the galaxy. But we would have evidence that they exist, and that alone would be the most transformative discovery in the history of our species. Conversely, if Tabby's star turns out to have a natural explanation, it would, in a sense, deepen the Fermi paradox. Here was our best candidate for a technosignature, and it was natural. This would not prove that alien civilizations do not exist, but it would suggest that detecting passive technosignatures is harder than we thought, that even the most extreme natural anomalies we can find can mimic the signatures of technology closely enough to mislead us. Either way, Tabby's star pushes the frontier of our thinking about our place in the cosmos. Before we move toward the conclusion of this exploration, I want to spend some time on something that is rarely discussed in the context of Tabby's star, but that I believe is deeply important. I want to talk about the star itself, not as a mystery, not as a vehicle for questions about alien life, but as a star, as an object in space, as a thing that exists independently of our curiosity about it, that has its own physics, its own history, its own future. KIC 846-2852 is an F-type main sequence star. It is approximately 1.43 times the mass of our Sun and 1.58 times its radius. It burns at a surface temperature of roughly 6,750 Kelvin, somewhat hotter than our Sun's 5,778 Kelvin. It is approximately 45% more luminous than our Sun. It is estimated to be somewhere between 800 million and 1.4 billion years old, younger than our Sun in absolute terms, but old enough to have potentially hosted planetary systems for hundreds of millions of years. It sits in the constellation Cygnus, the Swan, which lies along the Milky Way and is one of the richest regions of the sky for stars of all types. The star is close enough to be detected with the naked eye under perfectly dark skies, at magnitude 11.7, though only barely and only by experienced observers. For most people, it is invisible without optical aid. But with binoculars or a small telescope, it can be found, and once you know where it is and what it is, there is something extraordinary about pointing any optical instrument at that faint star and knowing what questions surround it. The star is part of a system. It has a distant companion, a faint red dwarf star catalogued as EPIC 217841697, which orbits at a distance of more than 880 astronomical units, almost 22 times farther from KIC 846-2852 than Neptune is from our Sun. The gravitational influence of this companion on the inner system is weak, but some researchers have suggested that over very long timescales, it could perturb the orbits of comets or other bodies in the outer reaches of the KIC 846-2852 system, sending them on trajectories that would bring them closer to the star. If there are planets in this system, we do not know their properties. The Kepler data, despite its extraordinary precision, has not produced a convincing planetary transit signal from this system. This might mean there are no planets, or it might mean that any planets present are not aligned in such a way that they transit the star from our vantage point, which is actually the much more likely scenario. Only a small fraction of planetary systems are aligned to allow transits to be visible from any given direction. The star is moving through the galaxy at a velocity consistent with its location in the galactic disk. It is not a runaway star, not a high-velocity object that would indicate an unusual past. It does not appear to have any unusual elemental abundances or spectroscopic peculiarities that would set it apart from other F-type stars of similar age. In almost every respect other than its dimming behavior, it is an ordinary, unremarkable star. This ordinariness is itself a kind of mystery. Most truly exotic astronomical phenomena occur in exotic stars. Bizarre behavior from a strange pulsar or an unusual variable star or a massive blue hypergiant makes a certain amount of sense. But an ordinary middle-aged F-type star doing something no other star has ever been observed to do? That is genuinely puzzling on a fundamental level. It raises the question of whether this is truly unique, of whether there are other stars in the sky doing the same thing but not yet discovered, either because we have not looked carefully enough or because the alignment of their orbiting material is not such that it transits toward Earth. The Kepler mission looked at a specific patch of sky with specific sensitivity thresholds. Tabby's star was the most extreme anomaly in that dataset. But the dataset covered only a small fraction of the sky and only for a few years. There could be dozens or hundreds of similar objects we have not found yet. Or this could be genuinely unique. We do not know. The upcoming test mission, the Transiting Exoplanet Survey Satellite, which has been observing since 2018, covers a much larger fraction of the sky than Kepler did and is monitoring a far larger number of stars. It is already producing data that can be searched for Tabby star-like anomalies. As of the time of this writing, no exact analog to KIC 846-2852 has been identified in test data, though a number of interesting anomalous light curves have been flagged for follow-up. The search continues, and the Rubin Observatory, currently under construction in Chile and expected to begin full operations in the mid-2020s, will observe the entire available sky repeatedly over 10 years with unprecedented depth and cadence. It will monitor billions of stars. If there are other stars doing what Tabby's star does, the Rubin Observatory will find them. And if it does, If we find not just one anomalous star but several or dozens, the statistical picture would change dramatically. If multiple stars show the same kind of irregular, asymmetric, secular dimming as KIC 846-2852, it becomes harder to sustain the idea that this is a rare, exotic natural phenomenon specific to one-star circumstances. A common signature, appearing around multiple stars of different types and ages, would suggest a common cause. And common causes are easier to study and characterize. The science would advance rapidly. But it would also raise the stakes of the megastructure hypothesis in a new way. If there are many stars dimming in this manner, and if megastructures are the cause, it would imply not just one alien civilization but many. It would imply that advanced civilizations building Dyson spheres are, in fact, reasonably common in the galaxy. And that, in turn, would make the Great Silence even more profound, even more mysterious. If there are so many advanced civilizations out there building megastructures around their stars, why are none of them communicating with us? Why are none of them visiting? Why are none of them in any way making their presence known beyond the shadow they cast on their star's light? These are questions that would not have easy answers. But they would be questions we would be forced to take seriously in a new way. Let us now, as we approach the final chapter of this exploration, ask the biggest question of all, the one that all of this has been circling around. Not, what is causing the dimming? Not, are there aliens? But the deeper, stranger question that lies beneath both of those. What does it mean to be a young civilization in an ancient universe? We are, by any measure, newcomers. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Complex multicellular life has existed on Earth for roughly 600 million years. Homo sapiens has existed for roughly 300,000 years. We have had writing for 5,000 years. We have had electricity for 150 years. We have had radio telescopes for about 80 years. And in those 80 years, we have gone from listening to our first crackle of radio noise from space to detecting gravitational waves from colliding black holes, landing machines on Mars, photographing a black hole 55 million light years away, and finding thousands of planets orbiting other stars. The pace of our development is astonishing by historical standards. But in cosmic terms, we are barely getting started. We are, to use a metaphor, a civilization that learned to light a fire yesterday and is now trying to understand a civilization that has been building cities for 1,000 years. If there are civilizations in the galaxy that have been developing for millions or hundreds of millions of years, they are to us as we are to single-celled organisms. Not in terms of their right to exist or their moral worth, which have nothing to do with technological sophistication, but in terms of their capability, their understanding, their relationship with the physical universe. They might perceive reality in ways we cannot conceive of. They might have solved problems that we do not yet know exist. And the things they build, if they build anything like the theoretical megastructures physics allows, would be as incomprehensible to us as a smartphone would be to a Neanderthal. This is not a reason for despair. It is a reason for wonder, and for humility, and for urgency. Because the flip side of this picture is that we are here, asking these questions, finding these data, looking at this star. We are a young civilization, yes, but we are a civilization that is already capable of detecting the potential signatures of civilizations incomparably more advanced than we are. The fact that we can even frame the question of whether Tabby's star is a megastructure, that we have the mathematics, the physics, the telescopes, the patience, and the intellectual framework to consider it seriously, is itself a remarkable achievement. We are not passive spectators in the cosmic drama. We are participants, observers. We are, in the language of one astronomer, the universe's way of knowing itself. Every photon that reaches our detectors from KIC 846-2852 has traveled 1,400 years to get here. It began its journey when the star released it, 1,400 years in our past, and it has crossed nearly 9,000 trillion kilometers of empty space to arrive at the precise moment when we have instruments capable of measuring it. The timing, from a cosmic perspective, is staggering. We live in the first moment in the history of our species when we have the technology to ask and potentially answer the question of whether other civilizations exist in the universe. This window in time is short, measured against cosmic timescales. And we are in it right now. That is not nothing. That is, in fact, everything. What happens next? What can we expect in the coming years and decades as the investigation of Tabby's star continues and the broader search for technosignatures expands? The near-term observational priorities are clear. More photometric monitoring of KIC 846-2852 to catch future dimming events. More spectroscopic observations during those events to characterize the absorbing material in ever greater detail. More infrared observations to constrain the thermal properties of the system. More searches for radio and optical signals from the direction of the star. All of this is ongoing or planned. The James Webb Space Telescope, which has now been operating for over 2 years and producing extraordinary science, has the potential to provide new insights. Its mid-infrared instrument, known as MIRI, can observe the thermal emission of material around other stars with unprecedented sensitivity. A detailed MIRI spectrum of KIC 846-2852 could reveal the mineralogy of the dust in the system, the specific silicate features that reveal the composition of the grains, which in turn would constrain their origin. Did they come from comets? From asteroid collisions? From something else? The answer would help determine which natural scenario, if any, fits the observations. Meanwhile, the theoretical work continues. New models of stellar disk physics, new simulations of cometary disruption and fragmentation, new calculations of the optical properties of different types of dust clouds, all of this is being done by researchers who take the mystery seriously. And theorists interested in the megastructure hypothesis continue to develop more precise predictions. What exactly would a partial Dyson sphere look like in terms of its photometric and spectroscopic signature? What would the infrared emission of a Dyson swarm in a specific orbital configuration look like? How would the dimming pattern of a Shkadov thruster compare to that of Tabby's star? These calculations exist in the literature. They make testable predictions. And as our observational capabilities improve, those predictions will be tested. The question of whether KIC 846-2852 is a natural phenomenon or something else is, in principle, answerable. We may not yet have the tools to answer it definitively, but we are developing them. The Vera Rubin Observatory will conduct its legacy survey of space and time, monitoring billions of objects over a decade with extraordinary cadence and depth. The Nancy Grace Roman Space Telescope, currently under development, will survey the sky in the infrared with a field of view 100 times larger than Hubble's. New generations of extremely large ground-based telescopes, the Extremely Large Telescope in Chile, the 30-meter telescope in Hawaii, will provide spectroscopic capabilities of unprecedented resolution and sensitivity. The Square Kilometre Array, under construction in South Africa and Australia, will be the world's largest radio telescope, capable of detecting radio signals far weaker than any previous instrument could reach. The next 2 decades will see a transformation in our ability to study the universe, and specifically in our ability to search for both natural anomalies and potential technosignatures. The probability that Tabby's star will still be a mystery in 2040 is not zero, but it is substantially lower than it was a decade ago. We are closing in on the answer, and what an answer it might be. There is something I want you to do, if you are willing. Something more than just passively receiving this information. I want you to look up at the night sky, if you can, and find the constellation Cygnus. It is visible from the northern hemisphere throughout the summer and autumn months, and it is easy to find because its brightest stars form the Northern Cross, one of the most recognizable asterisms in the summer sky. The bright star at the top of the cross, at the tail of the swan, is called Deneb. It is one of the most luminous stars visible to the naked eye. And in the region of the sky surrounding it, invisible without a telescope, is Tabby's star. When you look at that part of the sky, when you trace the outline of the constellation and imagine the faint star hidden within it, you are looking at the most mysterious object in the known universe. You are looking in the direction of something that has baffled the best minds in science for nearly a decade. You are looking toward a place where, perhaps, something extraordinary happened. Where perhaps something is happening still, right now, in the present of whoever lives there, though we will not see it for 14 centuries. And as you look, ask yourself, what would it mean for you, personally, to discover that we are not alone? How would it change your sense of who you are? How would it change your relationship with the universe, with your species, with the night sky itself? Would it comfort you or terrify you or both? Would it make you feel small or part of something larger? Would it change what you believe, what you hope for, what you fear? These are not idle questions. They are the questions that Tabby's star forces us to confront, and they deserve to be taken seriously, not just by scientists and philosophers, but by all of us. Because the discovery, if it ever comes, will not belong to astronomers alone. It will belong to every human being who has ever looked up and wondered. It will be the answer to a question that has been part of the human experience since our ancestors first looked at the stars from the mouths of their caves. We have always sensed that we are not alone in this vast cosmos. We have always hoped and feared that somewhere out there, something is looking back. Tabby's star is the first, clearest, most stubborn hint that we might be right. There is a final dimension to the story that we have not yet fully explored, and it concerns what happens to the scientific community and to public discourse in the period between discovery and resolution. In the years since 2015, the debate around Tabby's star has played out in an environment very different from the one in which most previous scientific controversies unfolded. Social media, online forums, YouTube channels, podcasts, subreddits dedicated to astronomy and to alien life. All of these have created a parallel public discourse that runs alongside the peer-reviewed scientific literature and sometimes interacts with it in complex and not always productive ways. On one hand, this public engagement has been tremendously positive. The Planet Hunters project, which found the star in the first place, is itself a product of this kind of public participation. The Kickstarter campaign that funded the 2017 Observing campaign demonstrated that ordinary people are willing to put their money where their curiosity is. The broad public awareness of the mystery has ensured that it remains a priority for telescope time and funding in a scientific world where competition for resources is intense. When millions of people are watching a star, it is easier to argue for the resources to keep watching it. On the other hand, the social media discourse has also produced a significant amount of misinformation, wishful thinking, and conspiracy theorizing. There are corners of the internet where Tabby's star is treated not as an unresolved scientific mystery but as confirmed evidence of alien civilization, where anyone who expresses doubt about the megastructure hypothesis is accused of being part of a cover-up, where sensationalized claims and fabricated details circulate alongside genuine science and are often more widely shared. This is not a new problem in science communication, but the scale and speed of social media amplify it in ways that can be genuinely harmful. The challenge for scientists, science communicators, and thoughtful members of the public is to maintain the spirit of genuine openness that the mystery demands, to avoid both premature certainty that it is aliens and premature certainty that it is not, while also maintaining the standard of rigorous evidence that science requires. This is harder than it sounds. Human beings are not naturally comfortable with sustained uncertainty. We want to know. We want resolution. We want to classify things into bins: real or not real, natural or artificial, mundane or extraordinary. The honest answer, we do not yet know, is psychologically unsatisfying in a way that drives people toward premature closure in one direction or another. The best scientists who have worked on this problem have modeled how to hold open uncertainty with intellectual integrity. Boyajian, Wright, Montet, and others have been consistent in acknowledging what the data show, what they do not show, what could change the picture, and what remains genuinely unknown. They have been willing to say, "This is strange and I don't understand it," without leaping to the most dramatic conclusion. And they have been willing to say, megastructures are a possibility worth considering, without allowing that consideration to distort their evaluation of the evidence. This is, in many ways, a model for how we should all approach the big questions. Not with premature certainty in either direction. Not with the cynicism that dismisses extraordinary possibilities out of hand. Not with the credulity that accepts them without evidence. But with the genuine, sustained, disciplined openness that says, I do not know the answer, but I am going to keep looking, keep asking, keep testing, until the answer reveals itself. That is what science is. And Tabby's star is one of its finest current examples. Let us, as we move toward the end of this journey, take one more sweeping look at the full landscape of what we have explored. We began with the discovery of a star that defies explanation. We traced the path from its identification by citizen scientists to its emergence as the most debated object in modern astronomy. We examined the specific anomalies in its light curve, the dramatic dips, the asymmetrical profiles, the long-term secular dimming, and the wavelength-dependent characteristics that tell us something about the nature of the obscuring material. We explored the natural explanations, the comets and dust and disk models, and found each of them partially but not fully satisfying. We considered the extraordinary alternative, the alien megastructure hypothesis, and took it seriously as a scientific proposition while maintaining appropriate skepticism about its likelihood. We traced the scientific and cultural response to the star's discovery, from Jason Wright's careful paper to the global media phenomenon to the crowd-funded observing campaign. We explored the broader context of the search for extraterrestrial intelligence and the concept of technosignatures. We thought about the philosophical and existential implications of both possible answers. And we looked ahead to the future of the investigation and the tools that might finally resolve the mystery. Throughout all of this, one thing has remained constant. The star is still there, still dimming, still brightening, still producing data that our best models cannot fully explain, still waiting for the question it poses to be answered. And this, ultimately, is what makes Tabby's star not just scientifically important but narratively compelling, not just intellectually interesting but emotionally resonant. It is a story without a definitive ending, a mystery still in progress, a question that has been publicly posed and not yet publicly answered. And in a culture saturated with quick conclusions and instant gratification, there is something genuinely rare and precious about a mystery that refuses to resolve, that keeps opening new doors every time you think you are about to close one. The universe is very good at keeping its secrets. It has had 13.8 billion years to practice, and we have had only a handful of decades to seriously try to uncover them. The humility that this disparity demands is not defeatism. It is wisdom. We are young. We are learning. We are getting better at asking questions and at building the tools to answer them. And the universe, vast and ancient and indifferent as it is, occasionally offers us a glimpse of something that makes us lean forward, makes us squint, makes us say, wait, what was that? What just happened to that star? And we chase it. We always chase it. Because chasing is what we do. Curiosity is what we are. The desire to know is as fundamental to human nature as the heartbeat, as the breath, as the dream. Out there, 1,400 light years away, in a direction that you can find tonight if the sky is clear and you know where to look, there is a star casting a shadow. And we do not know what is making that shadow. We do not know if it is ancient ice and rock tumbling in cosmic orbits, or if it is something that no natural process has ever made. We do not know if it is a story of physics or a story of civilization. We do not know if we are looking at the past of a star or the future of ours. But we are looking, and we will keep looking until we know. That is the promise of Tabby's star, that the question will be answered. Not today, perhaps not in the next year, perhaps not for a decade. But the answer is out there, encoded in the photons that are even now crossing the galaxy toward our instruments, carrying in their wavelengths the truth about what is casting that shadow. When those photons arrive, When our telescopes catch them and our detectors measure them and our scientists analyze them, the answer will emerge. And whether that answer is natural or unnatural, ordinary or extraordinary, it will change something in how we see the universe. It will add a new piece to the picture of what the cosmos is and what it contains. And in the long history of our species, in the long story of our looking up and wondering, that moment will be remembered. Whether it turns out to be the moment we realize we are alone, or the moment we realize we are not, it will be a moment that defines us. So the next time you step outside on a clear night and look up at the sky, find Cygnus. Find the Northern Cross. And think about that faint, unremarkable-looking star that sits among its neighbors in that rich band of the Milky Way, hiding in plain sight, doing something that no one can explain. Think about the light traveling from it right now, crossing the void between stars, carrying its message toward us. Think about the scientists who are watching for it, year after year, patient and persistent and full of that very human refusal to stop asking why. And ask yourself, of all the things in this universe that could be the most important discovery in human history, why not this? Why not now? Why not us? Because the universe has been around for 13.8 billion years, and it has never, not once, bothered to explain itself to anyone. But it has occasionally, if you look carefully enough with the right instruments at the right moment, given us a hint. A shadow on a star, a dip in the light, a mystery 1,400 years old, arriving at our doorstep in the form of data, waiting to be understood. And we are, at this moment in history, for perhaps the first time, just barely smart enough, just barely equipped enough to begin to understand it. That is not a small thing. That is, perhaps, everything. There are those who have said that the discovery of extraterrestrial intelligence, if it ever comes, will be the loneliest discovery in human history. Because we will know that someone else is out there, that the universe is not empty, that the long silence has an end. And yet we will not be able to reach them. Not in any meaningful human sense. We will know of them the way you might know of a civilization on the other side of a wall too thick to penetrate. Aware of each other, unable to speak. Others have said it would be the most liberating discovery possible, that the knowledge of another intelligence in the cosmos would expand our sense of what is possible, would give context to our own existence, would inspire us to think on longer timescales and grander scales, that it would be, paradoxically, a deeply humanizing moment. The moment we became fully aware of what it means to be one species among many, one mind among others, one civilization among the civilizations that the universe has somehow managed to produce from hydrogen and time. Both of these responses seem right to me, and neither of them is quite right, because the reality of such a discovery, the actual experience of it, would be something we cannot fully anticipate. It would reshape us in ways we cannot predict. It would raise questions we cannot currently formulate. It would be, in the truest sense, unprecedented. Tabby's star stands at the threshold of this possibility. It is not a confirmed discovery. It is not a proven signal. It is a mystery. A deep, strange, persistent, beautiful mystery that has already changed the conversation, already pushed the boundaries of what we ask and what we look for, already made the search for intelligence in the universe more scientifically legitimate and more urgently conducted than it has ever been. That is its gift to us, whatever its ultimate explanation turns out to be. The gift of the question, the gift of the looking, the gift of not knowing, and knowing that it matters to find out. Somewhere, 1,400 light-years away, a star is dimming and brightening in patterns that have no name. And we are watching. We are watching. We are still watching. And we will not stop.